Okay, well, you're preparing for your test on electron arrangement. You've read Chapter 4 in your textbook. You have several worksheets, notes, videos available to you about the arrangement of electrons. And now you're working on the study guide. Make sure that you have your periodic table handy. Let's begin with some of these definitions. The valence electrons are the s and p electrons from the highest energy level. These are the outermost electrons. These are the same electrons that are displayed in the Lewis dot notation. An octet is a complete set of 8 valence electrons. The noble gases have a complete set of 8 valence electrons. That's an octet. We talked about several scientists and their models of the atom. Bohr is the one who said that there is a core, and then surrounding the core, the electrons orbit the nucleus. It's very primitive, and we know now better because of quantum mechanics that that's not quite true, but it still helps to draw out those energy levels in this way using the Bohr model. The next one asks, what's the difference between 1s and 2s? This is a very simple question. It's only for you to recognize that 2s is energy level 2, where 1s would be energy level 1. Now for the 3 principles. These are the 3 principles that guide the creation of the orbital notation. Do you remember this assignment? Because when we did this, we were filling in the electron configuration. 1s2, 1s, 1p2, and so forth. At the bottom are the explanation of those 3 principles. So in referring back to the bottom of that former worksheet that we did, you'll have those answers. Make sure you know the difference of these 3 so that you can answer the question correctly on the test. Remember that this is a video that can be paused at any time. The periodic table provided here on your study guide demonstrates the order in which the orbitals are filled. Reading from left to right, top to bottom, it goes through 1s2, then through 2s2, across to 2p6, next 3s2, across to 3p6. After 4s2, the D block drops back 1 level. So instead of 4D, we have 3D, 10, because it's 10 across, and then back to the 4th energy level, 4p6. Next is 5s2, 4d10, 5p6. At the 6th energy level, there's a break because of the F block. It goes 6s2, 4f14, because the F block drops back 2 energy levels, then back to the D block, which dropped back 1 energy level, 5d10, 6p6, 7s2, down to the F block, 5f14, back to the D block, D, 6d, 10, and then finally 7p6 if there were electrons there. So if there were a question about the order, it would look something like this. Now as to the shapes, you'll recall that the periodic table is sectioned off into 4 main blocks. The S block are all spherically shaped electron orbitals. There is one shape of sphere. The P block, on the far right-hand side, is made up of 3 different shapes. These are referred to as the dumbbell shapes. Each dumbbell shape houses 2 electrons. 3 times 2 is 6. In the D block, in the center of the periodic table, there are 5 different shapes that are called 4-lobed. Each of the 5 shapes can accommodate 2 electrons for a total of 10. And then down at the bottom, for the F block, there are a total of 7 different funky shapes for a total of 14 electrons. So in completing question 8, what are the shapes? That would be sphere-shaped for S, dumbbell-shaped for the P block, 4-lobe-shaped for the D block, and finally, funky-shaped for the F block. Number 9 says to draw the lines or boxes below for the correct number of suborbital sets. This refers back to orbital notation, and we have to have dashes in order to draw the arrows. This is simply what the question is referring to. It would look something like this. Because of the number of shapes, the number of dashes would be 1 for the s orbital, 3 for the p orbital, 5 for the d orbital, and 7 for the f orbital. On each dash, there can be 2 arrows, a clockwise spinning and a counterclockwise spinning, representing the 2 arrows that can fit into each suborbital. A complete suborbital has 2 electrons. If we had a partially filled suborbital set, say the p suborbitals, and there were 4 instead of a full set of 6, then we would fill all of the clockwise spinning first, 1 in each of the 3 dashes, before going back to repeat with a downward pointing arrow for the counterclockwise electrons. That's following Hund's rule. In this case, we wind up with 2 half-filled orbitals because they only have 1 electron instead of the complete 2 electrons. All that being said, 10 and 11 are pretty easy to answer. What is the number of suborbitals each block accommodates? That's the 1, 3, 5, 7. Since each holds 2 electrons, the answer to 11 is 2, 6, 10, 14, which corresponds to the number of elements going across for each of those blocks. Number 12 we just answered previously, but I'll remind you again. This is the correct order in which the atomic orbitals will fill, according to the Aufbau principle, going through the periodic table from left to right, row by row. Next are some pretty general questions. This one asks you to identify the element. If you go to the 3rd row in the P block and find the 3rd one over, that'll answer the question. The direction of the electrons, you know that that's clockwise and counterclockwise. You can spell those words out if you want. Number 15, valence electrons are the blank energy level of electrons. Highest, which means it'll always be the s and p electrons, because the D block drops back a level and the F block drops back 2 levels. S and P will always be the highest energy level electrons. Okay, number 16, Lewis dot notation. These are based on the valence electrons. Do you remember this activity? We represent the s electrons, both of them on the right-hand side of the element. The p electrons, go in a pattern around the left-hand side of the element symbol, up, left, down, the first 3 representing clockwise, the second 3 representing the counterclockwise. Boron has 3 valence electrons. Silicon has 4 valence electrons. Sulfur has 6 valence electrons, 2 in the s suborbital and 4 in the p suborbital. It's the 4th element over in the p block. And then we've seen phosphorus before. We know that it has 5 valence electrons. If any of these were noble gases, such as krypton, they would have a complete octet of valence electrons, a full set of 8, the 2 s electrons, and all 6 of the p electrons, 3 clockwise and 3 counterclockwise. Identifying the elements based on their orbital notations is as simple as finding the location on the periodic table. I suggest that you go to the final position, the final arrow representing the final electron, and identify the element that way. So this one will be in the 2s block, the 2nd row down, the 2nd element over. On this one, we would go to the 2nd row and go to the far right element in the p block because it has a complete set. Having a complete set of s and p is a clue that this will be a noble gas. This element only has 2 electrons, obviously that's helium. And then finally, we're going to the 3rd block, the 2nd element over, to identify this particular element. On number 18, they give us the electron configuration of an element and then ask us pertinent questions about it. How many electrons are in the 3rd energy level? Well, there are 2 in the s, 6 in the p, and 10 in the d of the 3rd energy level, for a total of 18. B, what is the highest energy level? Well, 4 is a bigger number than 3, So the answer must be the fourth energy level is the highest. The highest energy level are the ones that contain the valence electrons. You'll notice that there are 2 in the S and 5 in the P, for a total of 7 valence electrons. Is this element a noble gas? Well, no. In order to be a noble gas, it would have to have an octet of electrons, not 7 electrons. What is the atomic number of this element? If you add all of these little superscripts, that will give you the total number of electrons. Total number of electrons equals total number of protons, and that will tell you the atomic number. Or you can go on the periodic table, go to the 4th row, the P block, the 5th element over, and read which element it is and its atomic number. In G, we're drawing the orbital notation. We're translating the electron configuration into a set of arrows. But we have to label it. We only put the level and the block beneath the line, which would look something like this. Then, when we fill in the electrons, nope, I almost forgot that 3D drops back one. There we go, 4P. We do the clockwise first, and then the counterclockwise for that suborbital. When that suborbital is completely filled, we can advance to the next suborbital. When we get to 2P, we have to fill in all of the clockwise spinning before we can fill in any of the counterclockwise spinning. And it proceeds thusly, all the way across. When we get to 4P, we notice that there are only 5 electrons. So you put 3 going clockwise. That leaves us a remainder of 2 to go counterclockwise. You'll notice that there is 1 half-filled electron orbital. Anytime there's a half-filled suborbital, it cannot be a noble gas. We saw questions similar to this one when we did the electron configuration fun homework on Wednesday. Here are a couple of examples from that worksheet. You just follow the periodic table in order from left to right until you arrive at your target element. It's like playing Candyland and going from space to space. Remember, in orbital notation, you have to put at least 2 electrons in each suborbital, but you have to fill them in order. No skipping ahead. That would fall under the Pauli exclusion principle. On the part where you're doing noble gas configuration and Lewis dot notation, again remember that we have examples on that electron configuration fun worksheet from Wednesday. But here on the study guide itself, we have this handy dandy chart that gives 3 steps on how to write an appropriate noble gas configuration. Since arsenic is on the 4th row of the periodic table, the noble gas on the previous row is argon. That's a coincidence that both of these start with the letter A. Past argon, the configuration continues. 4s2, 3d10, and since arsenic is the 3rd one over on the 4th level in the P block, it would be 4p3. The Lewis dot for arsenic is going to be based on the electrons in the highest energy level, 4 S and P. There are 2 plus 3 electrons, a total of 5. So we would write the element symbol for arsenic, AS. We would put the 2 dots for the S electrons on the right, and then for the 3P, we would put 1 on the top, 1 on the left, and 1 on the bottom to represent each of the 3 shapes of the P block, those 3 dumbbell-shaped suborbitals. You can imagine there will be a couple of review questions on the test concerning the calculations for the energy of electrons. We used the equation C equals the wavelength times the frequency quite extensively. You need to use algebra in order to rearrange the equation. Since you're given the speed of light in each case, we have the value of C. In 23 and 24, we're given the wavelength. In 25, it's a little different. We're given the frequency. But the basic idea is still the same. Using algebra, if I need to solve for the frequency, then I need to set the equation so that frequency is the only thing on that side of the equation. Therefore, frequency is calculated by taking the speed of light, c, divided by the wavelength given. If I'm doing the other way around, and I'm trying to calculate for wavelength, these two wind up switching places, and it becomes the wavelength is equal to the speed of light divided by the frequency. Essentially, you're going to take the speed of light, divide whichever value you're given, and that will solve for the one you're not given. Remember, number of significant digits in the given information, not the constant, will determine the number of significant digits in the final answer. Check the answers at the bottom of the last page after you've done the work to see if you're on the right track. And then finally, conversions. It's important that you write the conversion factor correctly. The prefix given would mean one of those is made up of this number of the basic units. For example, in 26, we're asked to convert 4,500 milligrams to grams. That means I need a conversion factor to go from grams to milligrams. I set it up so that milligrams cross-cancels, and then I just need to fill in the values. According to this chart, milli means 10 to the negative 3. That means 1 milligram has a value of 10 to the negative 3 of the base unit, which in this case is grams. When you multiply 4,500 times 1 times 10 to the negative 3, you get 4.5 grams. On the second one, we're starting with liters. The conversion necessary is going to take us from liters to kiloliters. So you set up the units to cross-cancel. We need the value of either liter or kiloliter. We know that 1 kiloliter, according to this chart, is made up of 10 to the 3 liters. As a cross-reference, if we put the number 1 with the larger of the two units, which in this case is kiloliters, then the exponent with the other one has a positive value. Of course, there's always more than one way to do things. This could have been expressed as 72 liters, and the conversion factor would have then been, not kilometers, kiloliters, sorry about that. Okay, so I could say that 1 liter, now that liter is smaller than kiloliter, so when I put 10 to the 3 up here, I will put it to the negative value. 1 liter is 1/1000th of a kiloliter. Whether I multiply by 10 to the negative 3 or divide by 10 to the positive 3, I get the same answer. It's all about expressing that conversion factor in an appropriate manner. On number 28, going from micrometer to kilometer involves an extra step because you have to go through the basic unit to get there. So you start with the given micrometer. You'll convert from micrometer to meter, and then finally meter to kilometer. When you fill in the conversion factors, be mindful to use appropriate values. 1 micrometer has a value of 10 to the negative 6 meters. Just like 1 kilometer has a value of 10 to the positive 3 meters. So, go back, study well, make sure that you can fill in those electron configurations and do these conversion factors, and you could expect a good score out of 100 for this next test for your final grade of the 9 weeks. Good luck.